So the 500-pound weight in the middle of the shelf, how much of that weight goes to the outside here? 250. So there's really 250 pounds pulling down on each end of this. The wall carries this end, so the cable has to carry that 250. So what that means is the component of force here lifting up has to be 250 pounds because the cable has to match with an upward force, whatever the force is downward. So we have a triangle forming here where this is 250 pounds. But of course, the cable doesn't go straight up, so it has a horizontal component as well. How do we find the amount of that horizontal component? Well, yes, we know this angle right here is how much? 32 degrees, yes. This is vertical, this is vertical. That makes this a transversal through parallel lines. So those two angles must be the same. That would be a right angle because vertical and horizontal are always perpendicular. So this horizontal component here, I'm just going to call X. We're going to use tangent of 32 degrees equals X over 250. So we put that there over 1. We'll cross multiply and divide. Tangent 32 times 250 divided by 1 gives us a horizontal component of 156.22 pounds. Now to find the actual force on the cable, we'll call that P. We could do A squared plus B squared equals C squared, or we could come back and just use cosine of 32 degrees equals P over 250. Oops, wrong way. Should be adjacent of 250 over that hypotenuse of P. So we cross multiply and divide. 1 times 250 is 250 divided by the cosine of 32 degrees. 294.79 pounds. So that cable has to be capable of holding at least 300 pounds. Make sense? Any questions? Now, you guys are not going to be installing too many. This isn't totally impractical. I say you guys aren't going to be installing too many shelves, but you do deal with shelves if you get into like a head end and stuff like that, or an internal installing equipment and stuff like that. It can come up, but that's not, your internal equipment is not as huge as it used to be. You guys got that whole head end down there that's pretty much empty right now because all that equipment's going digital, right? Yeah. So the need to install heavy equipment on shelves is not what it used to be. But let's say a different end of the business. The utility pole. Let's say you've got a line on that utility pole that is, hey, some of you may end up doing it. Let's say that wire on that pole is, let's say it is mounted. Well, what's the standard height for mounting a wire on a pole? 30 to 40? 40 is a little high. No, we're gonna get to that. This is the actual strand, yep, the actual cable. Let's just go 30 feet. That actually is probably still a little bit high, but it works. Let's say that wire, what's your tensioning on the wire? Have you guys gone over that? No? Let's just say that wire is tensioned to 600 pounds. Now that sounds like a lot of tension, but if you guys ever, how far apart are those poles are like 150, 200 feet apart or more. If you ever take 200 feet of wire and just try to pull on the end, tie it to something on the other end, and pull on the end of it till you lift it up off the ground, I would be shocked if you had 200 feet of that wire, if you could actually pull hard enough to lift it off the ground. It takes a lot of force to hold that relatively flat. Now, if you tied one end up high enough, yeah, you could pull it, but there's a big sag in it. But to lift it so it has less than 3 or 4 feet of sag in that run, that takes a lot of force. So 600 pounds is probably on the low end of what you're tensioning those things. Now, to make sure, yeah, these posts can hold some weight, but if you don't reinforce it, if the wire connects in there and then no other direction, what's going to happen to that post over time? Well, it looks like it's already starting to tip the way I drew it, but it would be fine for a while, but slowly over time, that post is going to creep and tilt in the direction of that force. So what do we do to keep it from doing that? You do steel cable, called the guy wire usually, right? So let's say we've got that wire on there to reinforce it. Now, we usually try to hook that up as high on the pole as we can. I drew it in there poorly. I'm going to do it so it's hooked exactly even to where the 600 pounds is. The reason for that is it simplifies our calculation just a little bit if I do that. So in order to balance this pole out, that cable has to be tensioned so that it pulls with approximately 600 pounds here. So that wire is at 30 feet here. Let's say that we place it out this direction 15 feet, because that's all the farther we have in our right of way. If we go any further, we're going to be out of the right of way. So we need to know what is the force on that cable. To do that, we need to find one of our angles. Let's find this angle right here. How would I find that angle? Opposite and adjacent. So that trig function would be tangent. So we're going to use inverse tangent of 30 divided by 15. (63.43 degrees). That's 63.43 degrees. That makes this angle here, by the way, also 63.43 degrees. So if I look at that, if I think of this as being components like that, I don't care what that vertical component is. All I care about is what this total force on that wire is right now. So let's find that. If we're looking at that triangle, this is 63.43 degrees, and this is 600 pounds. I want to know that hypotenuse there. What sides do I have? Adjacent and hypotenuse. What trig function is that? Cosine. So cosine is 63.43 degrees equals adjacent of 600 over, I'm trying to find that hypotenuse, is C. Put this over 1 and I cross multiply and divide. So 1 times 600 is 600 divided by the cosine of 63.43. 1,341.41. So that cable has to be able to withstanding at least 1,341.41 pounds. So my guess is you probably use a 2,000-pound cable there, because over time strands are going to corrode and they're going to fray. I don't remember what the safety margin is on those cables, but it's somewhere around like 30-40% is your safety margin. So anyway, let's talk about this component right here that we didn't find. This vertical component. I'm going to call that Y. What would be the easiest way to find Y here? We could do a squared plus b squared equals c squared. We could do that. So y would be the square root of 1341.41 squared minus 600 squared. If we wanted to, we could have gone back and used the tangent as well. We get 1199.74, so basically 1,200 pounds going down. What that's telling us, the reason we need to know that is this pole here, by adding this reinforcing cable here, this guy wire, it balances out the force of this pulling that way, but it adds 1,200 pounds of extra stress pushing down on that pole, which means that pole has to be able to hold up that extra 1,200 pounds. Basically, it's like putting a 1,200 pound weight right on top of that pole and telling the pole it has to hold it up. Make sense? So that pole now has to hold its own weight plus the weight of that wire. So whatever half the span of that wire is for weight, it has to hold up. Plus it has to hold, like I said, that 1,200 pounds. Any questions there? Let's look at this in a slightly different viewpoint. Pretend that pole straight up. Let's look at 600 pounds of tension on that wire again. We're going to continue to put it at 30 feet. Let's say I've got this cable attached here again. Cable's at 30 feet. This time we know, let's say that we are told this is a 2,000 pound cable with a 40% safety margin. What does that mean? That means you have to subtract 40% from the 2,000 pounds is the rated strength of the cable. You have to subtract 40%. What's 40% of 2,000 pounds? 800. So that means you can only have 1,200 pounds of force on that cable. What that's telling us is maximum stress on that cable is 1,200 pounds. If we assume that we have unlimited right-of-way here, how far back from that pole do we have to put this anchor to hold the other end of that cable? Well, we've got a triangle here again. That's our components, right? We know this is 600 pounds here. That's 1,200. Can we find this angle? Yeah. This is the adjacent side. The 1,200 is the hypotenuse. That makes what trig function? Cosine. So it's the inverse cosine of the adjacent 600 over the hypotenuse of 1,200. Inverse cosine of that is 60 degrees. So this is 60 degrees. Now how do we find this distance? We know that's 60 degrees. We've got this 30-foot height. 30 feet, 60 degrees. Yes, we're going to do tangent now. Tangent of 60 equals 30 over x. Put this over 1, cross multiply and divide. 1 times 30 is 30, divided by the tangent of 60. It has to be 17.32 feet back. So at least 7 foot 4 inches back to make sure that we stay under that 1,200 pounds. What do you think? Well, this would be the way it would work if you're terminating a wire at a pole. If you're looking at up from above, if this is your pole, the wire goes off in one direction and then it's being brought down, it's being run down the pole into the ground, and your support cable or guy wire goes off in this direction to hold it. But another common application we get And if you watch, if you pay attention, you'll see this, on a road. Let's say you've got a road that curves, and you got a pole here, a pole set up like this, where I'm going to move this on a little bit. So your wire is going off to those other poles. Don't come straight off each side. So the question is, how much force has to be balanced out? Assume again that each of these is 600 pounds of force. Assume the angle between them here, let's go 130 degrees. What I am going to do is this. I am going to pick one of them to be the 0-degree direction. The reason I'm doing that is it makes life a lot easier. So I'm going to redraw this picture. Off to the side here, here's my pole. There's 600 pounds here at 0 degrees. This 600 pounds is at what angle? 130. I need to do a vector addition. So for my vector addition, come on. I've got my 600 pounds at 0 degrees, 600 pounds at 130 degrees. Need to find px and py. Well, for the 600 pounds at 0 degrees, px is 600, py is 0. Because there is no vertical component of that at 0 degrees. Sine of 0 is 0. For my 600 pounds at 130, my px is 600 times, horizontal is always cosine. Py then would be 600 times sine. So 600 times cosine 130 is a negative 385.7. We're just going to call it a negative, we'll go negative 385.7. And then 600 times sine of 130, 459.6. So what that tells us is our total 600 and a negative 385 is what? 214.3. 0 and 459 is 459.6. So what we have is from that starting point, we have 214 this way, 0.3, 459.6 this way, giving us a total here. How do we find that total magnitude? Pythagorean. Square root of 214.3 squared plus 459.6 squared. $507.1. Then we need to find this angle here. That angle is going to be inverse tangent of vertical 459.6 divided by horizontal 214.3. 65 degrees. So what that means is to balance this out. What that means is on this post, the net force is right here of 400 or 507 pounds. And that this angle is 65 degrees. So we need to put that support wire in at the opposite direction. It has to be able to support 507 pounds. The opposite direction is going to be defined as 180 degrees this way. Well, what's 180 minus 65? 115. So from this force, actually it'd be 115 from this direction as well, by the way, because those forces are equal. But anyway, from this wire, we need to go 115 degrees this way to put in that support cable. And then we need to make sure that support cable can hold 507 pounds. We actually need to tension it. We'd have to tension it again so that it had a 507 pound horizontal component. We'd have to figure out what that overall tension would have to be. Make sense? Another application of this. Let's say, most of the time when you put in these guy wires, you actually bolt through the post. You don't put an anchor in. But let's say you have a ground anchor. Obviously, you can't bolt through the earth, right? Most of those turn in. They spin in like an auger, and they just stay in there once you got them down. Let's say that that ground anchor is capable of handling a force of 800 pounds straight up. If I put a support cable on here, let's say this here from the horizontal is a 55-degree angle. And this cable has 1,200 pounds on it. Is that anchor going to hold? Well, I'm going to take that 1,200 pounds, and what I'm going to do is this. I'm going to make a triangle. This is the 1,200 pounds. This angle here is actually 35 degrees. Where did I get 35? Yeah, there you go, 90 minus 55. I want to know this component right here, my y component. That's going to be a cosine. Cosine of 35 degrees equals y over 1,200. So to find that y component, I'm going to cross multiply and divide here. So 1,200 times cosine of 35 degrees. I don't have to divide by 1. I get 982.98. I get basically 983. Is that anchor capable of holding that? Oh, that's more than 800 pounds. This cable is going to be actually pulling up with 983 pounds of force that exceeds the 800 pounds. So we need a deeper anchor, a longer anchor. Does that make sense? Most of these, they assume that there is no lateral movement in it. That depends on the soil type. If you have sandy soil, then you have to account for lateral movement. A lot of times what they do is they put them in at a slight angle to account for the sandy soil. So because if it gets pulled past vertical, once it starts to pull like this, obviously now that cable pulling on it is more direct, so the component along the axis of that anchor is going to be even bigger. So they'd rather have them tilted this way, but technically those anchors are supposed to be as close to straight down as you can get them. But they do tilt them a little bit just to have a fudge margin there. Oh, let's see, what else do we want to play with? Just for fun, since Ian isn't here. Let's say that Mark has had enough of Ian. Bart, oh, we don't want to get too close to reality. Let's do this. Let's say that Bart has decided he's going to scare Ian into action. Did he? That's the trampoline, yeah. See, my art doesn't suck horribly. Okay, it does, but we'll pretend. Just to be safe, we'll give poor Ian a helmet. We're going to try to shoot him into the trampoline. So we're aiming our cannon at an angle here of 40 degrees. The cannon, we've tested the cannon, and the cannon, as long as Ian's aerodynamics aren't too messed up, is going to fire Ian out at a velocity of 200 feet per second. Well, we got to figure out how far away do we want to put our trampoline for him to fall on? Well, we need to look at trajectories. Trajectories have horizontal and vertical components. So we need the vertical component of his velocity. The vertical component would be 200 feet per second times the sine of 40 degrees, which is going to be 128.6, we'll call it. It's just his life. We can round off a little bit, right? That is feet per second. The horizontal, (200 times the cosine of 40). Do we expect that to be smaller or larger than the 128? Yes. At 45 degrees, we would expect the two to be equal. If the angle is lower than 45, the horizontal should be bigger than the vertical. (153.2 feet per second). So the first thing we need to figure out is how long Ian's going to be in the air based on this formula, based on that vertical speed. The formula for hang time, the height in the air is equal to V naught times T minus 16 T squared. V naught is the initial vertical velocity. What height is Ian going to be at when he lands? Well, we're going to assume that the mouth of the cannon and the trampoline are at the same height. So what height would he be at when he hits the trampoline? 0, right? 0 feet above the mouth of the cannon. So 0 equals 128.6. That's our initial vertical velocity times T minus 16 T squared. How do you solve a quadratic like this? Remember from last semester? It was only like 18 weeks ago. We factor it. We can factor out a T. So that's T times 128.6 minus 16T. So if that equals 0, one of those factors has to equal 0. Well, this factor T equals 0. That makes sense. T equals 0. When we fire the cannon, that's T equals 0. He's at 0 feet. Makes sense? That's not the one we want. We want this one, 128.6 minus 16T equals 0. So we are going to subtract 128.6 from both sides. So we got negative 16t equals negative 128.6. And then divide by negative 16. So 128.6 divided by, notice I left the negatives off, but a negative divided by a negative is a positive. Ian will be alive for, well, not alive, will be in the air for 8 3/80 of a second. If we do our calculations correctly, he'll still be alive. He'll just be in the air that long, right? So 8.375 seconds. So then the formula for how far he's going to go horizontally is distance equals velocity times time. What's his horizontal velocity? 153.2, right? Times, what's his time? 8.0375. We multiply that out. Get 1,231.3 feet. So from our cannon, technically we should go from the mouth of the cannon, right? To the center of our trampoline, we're going to go 120 or 1,231 feet 4 inches, or 1,231.3 feet. The center of the trampoline, and we'll be nice. We'll use like a 16-foot trampoline, so there's 8 feet leeway on either side. If he's more than like 7 feet short, though, he's going to land on the bar. That might hurt. Unfortunately, we didn't account for wind resistance, so poor Ian's going to fall way short of that. Any questions on that? You can see how those vectors play into that. That's right here. Let's look at a ramp. You're unloading a truck. This ramp, let's say, is a 34-degree inclined plane. You guys familiar with coefficient of friction? Coefficient of friction. Let's say this is the ground here, and you have a box that you're trying to drag across the ground. Let's say that box is 200 pounds, and the coefficient of friction is 0.3. As you are trying to pull that box in this direction, friction is pulling the other direction. It's resisting movement. The force that friction exerts on that box is its weight times that coefficient of friction. So 200 pounds times 0.3 is 60 pounds. So you have to pull with at least 60 pounds of force to drag that box across the ground. Make sense? Now that calculation worked here because the weight of the box is perpendicular to the ground. It's what's called normal to the ground. Let's put that same box on an inclined plane. 200 pounds. We need to know what is the component of that 200 pounds that goes normal or perpendicular. F with the little upside down T is perpendicular, and the force of that weight that goes parallel to the surface of the plane. So what we have here we know the 200 pounds goes this direction, right? So what we're going to have is a triangle that looks like this. This is 200 pounds. The perpendicular force goes this way. The parallel force goes that way. This 34 degrees is not going to be here, is it? That would be this angle right here, which is going to be what? .56. Good. So I want to find the normal force here. That's the opposite side, which implies we're going to use, this is the hypotenuse, right? So we're going to use sine. Sine of 56 is going to equal the opposite over hypotenuse. So sine of 56 times 200, or 200 times sine of 56. 165.8. Come on. Parallel component here, that would be the adjacent side. We're going to use cosine of 56. Equals the parallel component over 200. Once again, cross multiply and divide 200 times cosine of 56. 1184. 111.8 we'll call it, pounds. What is the normal force of friction here? Still using 0.3, we're going to use this amount, part that's perpendicular to the surface. Find friction. So friction is 165.8 times 0.3. 50 pounds, basically, 49.7 pounds. So is this box going to stay sitting there, or is it going to slide down the ramp? Gravity is pulling down, right? So friction is going to oppose that. Friction is going to pull this way at 49.7. Which force is bigger, friction or gravity? Gravity. So the box is going to slide down. If you were trying to pull the box down the ramp, obviously you wouldn't have to pull. It's going to slide. If you're going to pull it up the ramp, here's the irony of it. If you pull up the ramp, you have to overcome the 111.8 pounds. But guess what friction does if you try to pull up the ramp? Friction changes directions on you, that little bugger. And friction goes the other way. Friction goes in the opposite direction of any potential movement. So you would have to add 49.7 pounds to that. To pull this up the ramp, you would have to pull up with 161.5 pounds to overcome friction. So at least 161.5 pounds. What do you think? That's not unusual. This, by the way, is why more of a construction application than a telecom application. But handicap access ramps, can only have, well, it's technically it's 1 inch of rise for every 12 inches of run, or 1 foot of rise for every 12 feet of run. There used to be a 1 foot of rise for every 20 feet of run. So they've loosened it a little bit. But that gives you an angle here, of course, of an inverse tangent, 1/12, only 4.76 degrees. On a wooden surface, if it's wet, the friction between the wheels of a wheelchair and a wooden surface, that coefficient of friction can go down as far as like a 0.08. So let's say you've got a, it really doesn't matter how big the person is, but let's say you've got a 200-pound person in a wheelchair. So 200 pounds going this way. You want to get those components, right? This angle here, so be careful. This is actually the 4.76 right here, isn't it? Degrees, because we're going in the right direction. So anyway, I should have gone the other side. That's okay. This is 200 pounds. I want to know what each of those forces are. Well, this one is going to be sine, 200 times sine, 4.76. This is going to be 200 times cosine, 4.76. I'm just going to use 5 degrees. So I get 17 here. And about 199 here. Well, the coefficient of friction of 0.08, 199 pounds times 0.08, that's 16 pounds. So you can see at 5 degrees, if I change that ramp to 5 degrees, there's 17 pounds pulling them down the ramp, but only 16 pounds of friction. What does that mean? That wheelchair is skidding down the ramp. Because there's actually 1 pound more of pull down the ramp than there is of friction to hold them on the ramp. So that's why they have such shallow angles for those things. 0.08 is an extremely small coefficient of friction, but wet wood is, I mean, I'm sure you've walked across wet green treated decks and slipped on it. It's very slippery. Okay, so you guys have that packet I gave you. I don't know if I gave you this page to work on yet or not. Page 393 to 395. 1 through 39, the odds. And then I'll have you do this one. I know I haven't given you yet. Page 397 to 399. 1 through 23, the odds. I'm guessing there's going to be questions on these. Will you guys be in class tomorrow then if you're going to the high school, or not sure? Okay. Thursday, what do you guys got going?